in the upper atmosphere where the temperature is very small. So, the speed of sound will also be very small. So, Mach 10 does not necessarily mean that you are going fast. It is not 10 times the speed of sound that you are used to here at the sea level. Okay. So, you have to be careful about these kind of things. What is Mach number defined with respect to? It is defined with respect to the C naught, which is, let us say, for ideal gas. So, for ideal gas we can write this as u naught over square root gamma r T naught, where this is the temperature scale. Okay. So, this is your Mach number. Okay. What does Mach number quantify? What does Mach number quantify? It is very difficult to sort of look at it in terms of speed ratios, because oftentimes when you are looking at flows which involve Mach numbers, which are compressible flows, you are more concerned about the energy in the flow than just temperature. Okay. So, a more intuitive, although it may not seem to you now, but a more intuitive way of looking at Mach number is actually to look at Mach number square, which is u naught square over gamma r T naught for an ideal gas, and you can write it as, let us say, half u naught square over half gamma r T naught, where this gamma r T naught you can write as gamma r T naught by gamma minus 1. Okay. So, here it is kinetic energy divided by, what is this? Okay, let us not use a let us use a gamma here. Okay. And then so, this is, what is gamma, what is R T naught by gamma minus 1 for an ideal gas? R by gamma minus 1 is CV, the heat capacity at constant volume. So, this is basically gamma into gamma minus 1 by 2 times internal energy. Okay. So, it is very important to say that Mach number is essentially the ratio between the kinetic energy of the flow and the internal energy of the fluid that is flowing. Okay. So, internal energy might be small. By bringing internal energy to be small, you can raise the Mach number, you do not always have to speed up. Okay. So, that is what Mach number is. There are other numbers that you can define. For example, you can take the surface tension coefficient, let us say, that is sigma. What are the units of sigma? What will be the units of sigma? Huh? What will be the units of sigma? So, if you recall our boundary condition, the interface condition we had, T dot n 2 minus T dot n 1 equals 2 H sigma n hat. Let us say sigma is uniform. So, H is what? H was, what are the units of this guy? This is 1 by length. Huh? This is 1 by length. What is T dot n? What are the units of T dot n? What are the units of T dot n? T is what? Stress. So, it is Newton per meter square, right. There you have 1 by length, Newton per meter square. So, what are the units of sigma? Newton per meter, right. So, you can define some sigma L naught. Sigma L naught is a force, right, and you can divide it, let us say, by rho u naught square L naught L square, let us not take L naught. So, this can define a dimensionless number for you. How do we expect to get these kind of dimensionless numbers? When we non-dimensionalize not just the governing equations, but the boundary and interface conditions as well. Okay. So, an important point for you to note is that it is not just about non-dimensionalization of governing equations, because eventually you are going to not solve for u, but you are going to solve for u star, p star. Okay. You are going to solve for these starred quantities which are dimensionless quantities. So, you need boundary and initial conditions for the starred quantities. So, you will have to non-dimensionalize the boundary and initial conditions as well. Okay. And when you do that, you are going to get numbers like this. Okay. You could also get sigma L over mu u naught over L times L square, which is basically sigma over mu u naught. That is also a dimensionless variable. Okay. And all these dimensionless numbers you can get when you non-dimensionalize your whole system of equations, not just the governing equations, but the boundary conditions as well. So, it is very important to know that boundary conditions and initial conditions also have to be non-dimensionalized. Okay. So, this ratio RE that we were looking at. So, RE is essentially inertial force over viscous force, or we also said that you can look at it as viscous time scale over inertial time scale. So, the rest of the course is structured in this fashion, where first we will discuss flows that have RE much less than 1. In RE much less than 1, the inertial forces are very small compared to viscous forces. Okay. The inertial forces are very small compared to viscous forces. What does this mean? What does this what are the implications of this on the governing equations? We will look at that. Then we will look at RE much greater than 1 scenario. Okay. We will look at RE much greater than 1 scenario. And so, most of the course will be discussion of these low Reynolds number flows, then high Reynolds number flows, because when we discuss high Reynolds number flows, you will see that there is a complication. You cannot just say, oh, 1 by RE is going to be small, so I will just drop the viscous terms. Okay, you have to be careful there. Another nuance that you should notice is that I have been taking the velocity scale. Let us say you have a velocity scale, okay, which basically says that what is the nature, what is the, let us say, nominal value of velocity at some point. Okay. For example, let us say I define a density scale in this room. Is the scale of that quantity the same as scale of change in that quantity? Is that necessarily going to be true? No. Okay. You will say probably density does not change appreciably in this room when I am speaking. So, the change of density does not have to be does not have to have the same scale as the quantity itself. Okay. So, whenever you substitute, for example, these guys, okay, whenever you take, let us say you take a reference value here, you have to be always careful that these scales that you are defining. So, this is what helps, this is what will help you choose a relevant scale of the problem. So, the relevant scales make the starred quantities order 1. This is a notation that I am going to use. Okay. This is a notation that I am going to use, which basically you might have seen in your time complexity calculation. So, this is order 1. Basically what it means is, if your scale is correct, to the problem that you want to analyze. As I said in the beginning, there is no correct scale, there is a convenient scale. So, here the correct word I am using to replace that convenient term. If your scale is correct with respect to the problem that you want to analyze, okay, then you can double check that after you get the result that, okay, my quantities are order 1, the starred quantities are order 1. Okay. For example, let us say you are trying to analyze flow past a cylinder, a very simple case, you are trying to analyze, there is a uniform flow coming and hitting a cylinder. Okay. Someone will ask you, okay, describe the flow here, and the distance here is, let us say, 200 times the radius of the cylinder. Okay. Or, and someone else comes and asks you, okay, tell me the velocity here, and this distance is maybe 1.01 times radius. Okay. The length scales are very different. The relevant length scale that you have to pick are very different. Okay. So, the quantities that you may get. So, if you are trying to analyze flow here by taking this length scale, you may end up by you may end up getting velocities which are non-dimensional velocities which are very small or very large. Okay, you may end up getting wrong or let us say not properly scaled dimensionless quantities. These reference scales should be actual reference scales, they should not be just some value that you are taking, and eventually that is making your analysis even more complicated. Okay. Let us look at a thorough example for that. Order 1, it means order 1, the quantity is order 1. Order 1 means it is anything from 1 to 9, let us say. It is like an order of magnitude. When you say something is orders of magnitude higher, okay, in fluid mechanics at least, in mechanics in general, what we mean is something is, if it is 5 orders of magnitude higher, it is basically 10 to the power 5 times the comparison that you are making. Okay. Yeah.
Can you explain the relation of RE with respect to time scale?
So, you mean you want to know the derivation of that. So, it is u naught L over nu. So, what are the dimensions of nu? What are the dimensions of nu?
That's dimensionless, right?
Huh? Nu, what are the dimensions of nu?
Square per second.
Meter square per second, right. So, you can make a time by doing this. Okay. So, this is what u naught by L over nu by L square. This is 1 by viscous time scale, this is 1 by inertial time scale. So, you get a viscous time scale by inertial time scale. Inertial time scale means time scales of its movement basically. Whenever we use the word inertial in fluid mechanics, we are mostly referring to the movement of the fluid particles. Okay. So, let us look at a example and do a thorough derivation of what is known as your Boussinesq approximation. Okay. We will do a thorough derivation of your Boussinesq approximation, and that will show you why it is important to take the relevant scales in your problem. So, the problem definition goes something like this here. So, you have, let us say, axis is your x y z or whatever, x1 x2 x3 whatever you want to take, and let us say you have fluid. Okay. You have fluid which may be restricted in a container or in a very large room or whatever. Okay. And you have some density changes between the points, let us say the points which are separated by a distance L, the density between them changes by delta rho. Okay. There is gravity here, and the typical value of density. So, remember this is the change in density from this point to this point. This is the change in density from between 2 points. The typical value of density, let us say, is rho naught, or the scale of density is rho naught. Okay. Knowing these things, what do you think will be the correct velocity scale in this problem? So, there is no flow until unless there is a density change. Okay. The fluid is just so this is like a natural convection problem where you have a gravity, and you may have situations where you have heavier fluid on top of lighter fluid, which we all know is not a stable configuration, and there will be some convection currents which are going to develop inside this. So, in this kind of a scenario, what do you think is the correct velocity scale going to be? How do we get a correct velocity scale in this kind of a scenario? So, what is the force that is going to result in the flow? What is that force that will be resulting in a flow? Let us say there is a fluid particle which exists, and the fluid particle has a density which is higher than the density of the surrounding fluid. Then it has what? Or let us say there is a fluid particle which has a density lower than the surrounding fluid density. What will happen? Buoyancy, right. So, there is a buoyancy force that will act on fluid particles due to their density being different from the surrounding densities. Okay. So, there is a buoyancy force which we can say which will have a scale of this per unit volume. The buoyancy force will have a scale delta rho g per unit volume, that is going to move your particle. So, as I said, whenever you are concerned with the movement of particle, what you have to consider is the inertial quantity, which is going to be rho naught u square. So, in this problem, if rho naught u square, actually I do not need to put a similarity sign, I can put an equality sign because I am trying to get reference scales, I am not trying to get actual values. So, from here what you can probably, hold on, are the units correct? No. So, this is going to be the correct units, right. So, from here what you see is that the correct velocity scale in this problem is actually this guy. Okay. If I had only given you a length scale and gravitational g, you would have said okay, root gl is the velocity scale, but that is not true. It is actually going to be weighted, the gl is weighted by this delta rho by rho naught, okay, which makes sense also. Why? Because if there was no delta rho, there is not going to be any velocity. So, the flow is actually happening because there is a density difference. The flow is actually happening because there is a density difference, and if there is a small density difference, the velocity is going to be small compared to GL. If you have a very small density difference, the velocity is going to be small. Okay. So, this is how you can actually derive from basic physical intuition, you can derive the correct length scales, velocity scales or time scales of the flow, and this is your correct velocity scale. And now, when we do this, okay, let us non-dimensionalize our governing equations. So, let us non-dimensionalize our continuity equation. Now, we cannot just start with del dot u equals 0 here, density is changing, density is not constant. Okay. So, we have to start with the full mass equation, which was this. Okay. We have to start with the full mass equation, which is this guy, and let us non-dimensionalize this. So, I will take that the density scale is rho naught, the velocity scale is this u which I have derived here, the length scale is L, and there is a pressure scale, let us say P naught. So, the time scale will be L over u. So, here I will get rho naught u over L del rho star over del T star plus rho naught u over L del dot rho u equals 0, del star rho star u star equals 0. So, rho naught u by L is common in everyone. So, the equation reduces to simply this. Coming there. So, as your friend hinted that there is a problem, you just got the same equation back from which you started in the dimensionless variables, because we took that the scale of del rho star by del T star we took as rho naught u by L. We do not have any delta rho happening here. Okay. So, the way you can get that is you can say that your original field, which the dimensional field rho is, let us say, some rho naught plus rho prime. What you can say is that there is a constant density field, on top of that there are fluctuations. Okay. You can assume anything that is varying as some constant plus fluctuations, right, just to eliminate any mean value, any nominal mean value, you can do this kind of a trick all the time. I am not making any comments about rho prime being smaller than rho naught or anything like that so far. Okay. This is something, this is a kind of decomposition you can always do for a field. Okay. Just like you have a pressure and a gauge pressure, right. if I take the value of pressure in this room, it is different at different points. I subtract the atmospheric pressure, then I will get the pressure fluctuation at different points. Okay, that is what I have done here. In that case, my rho star by rho naught is 1 plus rho prime by rho naught. Okay, but we know that the correct scale of rho prime is not rho naught. It is not rho naught, it is what? It is delta rho. So, I have to multiply by delta rho here, okay, and then I will write delta rho over rho naught, rho prime over delta rho, and this quantity I will write as rho prime star.
Sometimes the fluctuation.
Yeah, it is a fluctuation. Huh? We cannot? No, I said that rho prime is maybe smaller or larger, I do not know. Yeah, because rho prime is the fluctuation. Okay, rho prime is basically what is the difference between the density between these 2 points, or maybe at this point what is the difference in density at 2 different times. Rho prime is that difference. The correct reference scale for that difference is not rho naught, it is delta rho. So, the correct non-dimensionalization of this fluctuation is not rho prime by rho naught, but it is rho prime by delta rho. When is a non-dimensionalization correct? When it is convenient. When is it convenient? When the dimensionless parameter is going to be order 1. So, rho prime by rho naught you know is not going to be order 1, but rho prime by delta rho, just by the definition of delta rho, is going to be order 1. Okay. So, all of these are scales. Wherever I have written the scales, okay, these are not fields, they are variables. Okay. So, let us say rho minus rho naught, the scale of this is delta rho. So, these are actual quantities or values, they may have some numbers. For example, it may be 1 kg per meter cube, this may be actually 0.1 meters per second and things like that. These are not fields. Okay. These scales are not fields, these are just numbers by which we would like to divide our variables or fields to get dimensionless fields. Okay. So, be careful when you think about these variables, these guys, the scales, okay, they are not fields.
So that should be rho instead of rho star in the second line.
Hmm.
Rho is equal to rho naught plus rho prime. Then in the second line,
Yeah, you are right. So, it is rho star. Thanks.
So in the original derivation, where you've substituted for del rho only, you've substituted.
No, I have not substituted for del rho. What I have done here is basically I have just written rho is rho naught times rho star. Okay. But as we see that this does not give us anything more simple, it just leaves us with the same equation in the starred quantities. So, we are trying to say we are trying to see how to get that fluctuation scale or the change of density scale in this rho star, and from here you see that rho star is some 1 which is a constant plus delta rho by rho naught rho prime star. So, when I substitute this rho star here, then I am going to get those delta rho by rho naught values. Okay. So, that is where, so let us look at this. So, you have delta rho star by del rho star by del t star plus this guy plus this guy. Let us substitute this rho star here. Okay, let us substitute this guy here. What is del by del t of this guy? It is simply delta rho by rho naught. Okay. What about here? We have u and what about here? Okay. I can further simplify this part. I can write delta rho by rho naught del rho prime star by del t star, and then I can, so this gradient of this quantity is not, I mean this is constant, so it does not matter. So, we will get a u star dot del star rho prime star. I have taken delta rho by rho naught common outside, okay. And then from here we get a delta rho by rho naught rho prime star del star dot u star plus a del star dot u star equals 0. Okay. Let us write this also together. So, I have delta rho over rho naught del rho prime star by del t star plus del star dot rho prime star u star plus a del star dot u star equals 0. So, simply by writing this kind of a decomposition for density, what we have managed to do is we have managed to simplify this equation, or rather for now maybe it does not look simplified, it looks like it is more complicated, but we have managed to break it into two parts. Okay. We have managed to break it into two parts, and now we are going to use something which is again you will be expected to know throughout this course, and that is what happens to the flow in the limit when delta rho by rho naught is much less than 1. So, we will replace this delta rho by rho naught wherever I am writing, just for convenience purposes I will replace it with the with an epsilon, which is generally the variable used for a small parameter, and that is much less than 1. In this limit, what happens to the flow? In this limit, what happens to the flow? So, what you will see, what you will write here is, this is the continuity equation is actually del star dot u star plus epsilon times del rho star prime over del t star plus now that we have reached here, the way we read this equation is basically what we are trying to say here is that we are going to separate this, just like you probably, you guys, have you guys done power series solutions of governing equations of any ODE? Do you know how to calculate power series solutions? Yeah, we just write the solution is a n x to the power n, and then bring the coefficients of the same powers of x together and make them 0 individually. Okay. This is very similar to that. What we say here is that due to this smallness parameter epsilon, we have a governing equation which may have higher orders of epsilon, by the way. Okay. This equation could have higher orders of epsilon, it just turns out here it just has epsilon to the power 0 and epsilon to the power 1. It may have higher powers of epsilon, and the coefficients of individual epsilon powers, we are going to write them as 0, and they are going to give us a hierarchy of equations. That is, you will get at order epsilon to the power 0, that is how you write these, okay, which is also known as adds at leading order. In some textbooks you will see this written like this. At leading order, the equation is del star dot u star equals 0. What does this at leading order mean? What this at leading order means is that, let us say there is a flow happening here, there is some flow velocity field u. Okay. The velocity field is going to be divergence free at leading order. There is going to be divergence of that velocity field, but that divergence is going to have scales or values which are proportional to delta rho by rho naught. Let us say your delta rho by rho naught is 1e minus 5, okay, or 10 to the power minus 5. In those cases, the divergence of velocity field is going to be of order 10 to the power minus 5. Okay, that is what this at leading order equation means, that the equation is correct at leading order. Leading order means the equation is correct at the most significant, most or the highest significant digits, let us say. Okay, you are going to see some effects if you just take this as the correct governing equation. You are going to see some effects, some discrepancies in an experimental result, and let us say an analytical solution if you can evaluate. Okay. At leading order, this is correct. At first order or at the next order, the correct governing equation is actually rho prime star okay. Now the next order equation here is not giving us any relation is not giving us an equation of u star, it is actually giving us an equation of rho prime star, because u star is something that you have already evaluated. Okay. U star you have already said that its divergence is 0 at leading order. So here what we do is we open this up and we obtain the equation
So could you repeat the 10 to the power minus 5 example?
So, when I write this equation, okay, let us say the changes in density are very small. This equation is del dot u, forget about stars for now, del dot u plus 10 to the power minus 5 times this equals 0. Okay. So, original equation is this is what we have to satisfy always. Okay. I am saying this you can write as this, where you have a 10 to the power minus 5 times something. So, what I am saying is that if 10 to the power 5 minus 5 is 0, then this is the equation.
It's 1, right?
10 to the power minus 5. If 10 to the power minus 5 is 0, if you are going to accept it as small as 0, then this is the equation. Okay. Whatever result you get after using this and rest of the equations, okay, that result will be correct up to, let us say, 10 to the power minus 4, and the fifth decimal point or whatever numbers you are looking at, fifth decimal points in your actual experiment analytical solutions will vary, will be different, will not be same.
So we neglect the other coefficients or SL.
Yeah. So, what we are doing is when we do the individual coefficients to be 0, what we are saying is this is 0, this is 0, and if there are higher powers of epsilon, their coefficients are also 0, because this whole term summation has to be 0. And what we are saying is, so this quantity, if our non-dimensionalization is correct, this quantity is expected to be order 1. The quantity inside the bracket here is expected to be order 1. There is no way that this quantity could be balanced by this quantity, because it is multiplied with epsilon, which is small. You cannot balance an order 1 quantity with an order epsilon quantity. So, individually those equations have to be 0.
And it's carried forward also that the first leading question.
Yeah. Leading equation applies. Leading equation applies because the variables are same. If this u star was some other u star prime, let us say fluctuation over fluctuations in velocity, then I couldn't have written that del dot u star is 0. This is also something that we will do. What we will do is, we have a, let us say we have a smallness parameter in our problem. we will write our solution as some u naught plus epsilon u1 plus epsilon square u2 and so forth. Okay. This is something that we will consider when we go to linearization of the problem, which is not very different from what we are doing right now.
So can you again explain the rationale of saying that whatever is inside epsilon, the bracket of epsilon, and let's say del
So,
star,
this is order 1. If your non-dimensionalization is correct, this is order 1.
and you think that should also be order 1.
This is also order 1 without epsilon.
Okay.
But when you multiply it with epsilon, that is order epsilon. Okay. An order 1 quantity cannot be balanced by an order epsilon quantity. So, individually they have to be 0. Let us do the same procedure on momentum equation. Okay, this is a bit, so I understand if some of you are having difficulty in wrapping your head around it, this is a bit of an advanced discussion, but if you can understand this, you can ask me also, you can discuss.
So I was discussing ki, if divergence at a bigger scale is 0, does it mean that at a smaller scale it should be 0 or not?
So, I am applying the divergence to the same velocity.
Right.
The divergence is of the same variable. The smaller scale, from smaller scale you got the equation, but the equation is still in the same variables. If the variable had changed, then I could not say. Let us say, as I said, that if this u star, if this u star itself, I had expanded it something like this, and so on. And if I had written this only for u naught, then I cannot say it for u1. It is the same variable that I am commenting upon. Okay. So, be careful with, you are right that I cannot say it for the next scale, but for introducing the next scale you have to introduce another variable. Okay. What would that expansion mean? The u naught star plus epsilon u1 star plus so on. What it means is that you have a velocity that is happening due to density changes. On top of that velocity you have some fluctuations, which are order epsilon. Makes no sense actually, right? Because you are already accounting for that velocity that is happening due to fluctuations in u star. Why would I have another fluctuation of velocity? Okay, we are not entertaining any other sources of velocity of flow here. We are not saying the flow is happening due to pressure differences or anything. The flow is happening purely due to buoyancy effects. Density differences are all that are causing the flow.
Order 1 means dimensionless and dimensionless. So what do you mean by order?
No, dimensionless are they are all dimensionless. Order 1 means del star dot u star. If you expect given your non-dimensionalization is consistent, you expect this quantity to be order 1. Given your non-dimensionalization is relevant, you expect this quantity to be order 1. This is very similar to, let me give you an algebraic example, maybe that will help you connect it better. This is very similar to an example that we had taken earlier in, I think in the first lecture. Let us say this is the equation that you have, okay, where this epsilon is very small. Okay. How do you solve this equation? So, you let us say write it like this. Okay. After this, what will you say? You will say, okay, my x is some x naught plus epsilon x1 plus epsilon square x2, and then you will substitute this x, and then you will collect the powers of epsilon, same powers of epsilon, and that will help you find x naught, x1, x2 and so forth. Okay. What I am doing is just one step before this, okay, because I do not have x, I actually have equations now. I don't have just a variable, I have equations now. So, I am just telling you that at leading order I am saying x square plus 1 is 0, which is exactly what you will get when you substitute here x naught and you separate powers of epsilon 0. I am saying at leading order x square plus 1 is 0. That is what I mean when I say at leading order this del dot u star is 0.
So that is only valid if epsilon tends to 0, right?
Exactly. So, that is where, right, all of these things are, whenever I write something epsilon until unless otherwise specified, I mean that quantity is small. Okay. So, it should also tell you that if I am writing something dimensional as epsilon, that is nonsense. Okay. Something could be 1 nanometer, but is it small? We do not know, right. We have to know, we have to comment it, smallness or largeness are comparative terms. I cannot say 1 nanometer is small, compared to what is it small. Okay. So, if I am writing epsilon to be some dimensional quantity, please correct me, because that cannot be true. So, let us do this on the momentum equation, the whole procedure, and then we will derive some interesting conclusions. So, let me write the full momentum equation, because again I cannot just take the incompressible momentum equation and proceed with it, because the density is changing. Just like I did with continuity equation, I have to do the same, I have to do the same thing for momentum equation. I cannot just, or maybe I can just write in the non-conservative form. And then you will have, let us say, so mu I am taking always as constant. So, del dot 2 s minus 2 by 3 del of del dot u. This is what you will get when you substitute your Newtonian isotropic fluid stress with Stokes assumption, the full stress tensor, and there is a pressure term and there is a body force term, gravity is there. Okay. And this g vector is basically minus g j cap. Okay. Yeah, I am going to have to rub this. So, let us proceed with the non-dimensionalization. Okay. So, we have rho naught, and from here you will get a u square over L, and then a rho star times del u star over del t star plus u star dot del star u star equals minus p naught over L del star p star plus. So, this S was your symmetric part of velocity gradient tensor. So, essentially when you non-dimensionalize, you will get a u naught over L, okay, and there is a del dot as well. So, you have a mu u naught over L square, and then a del star dot 2 S star minus 2 by 3 del star of, and then we have a plus rho, let us say rho naught times g, and then a rho star g star, where g star vector will simply be minus j cap. Okay. It is not vector. So, let us divide things with rho naught u square by L. So, on the left hand side I am left with this So, I am going to combine this and this first. Plus mu, or this we know is going to be 1 by Re, and then the viscous terms. Okay, let us not bother about them as of now.
Rho naught G plus rho dash G dash
Hmm?
on the top, in the end, what side?
Where?
Rho naught G, rho dash.
Rho naught G into rho star G star. G star is the non-dimensionalized acceleration due to gravity, which is just minus j cap. Oh. So, what is the pressure scale that you expect in this problem? Just like we have derived a velocity scale, what is the pressure scale that you expect in this problem? Whenever you have gravity and you have a fluid which is basically resting due to that gravity, there is no flow, what is the pressure scale that you expect in this problem? Hydrostatic pressure. Okay. So, the pressure scale in terms of the existing scales you can write is going to be this guy. Okay. The correct pressure scale, not the pressure fluctuation scale, remember, this is not the correct pressure fluctuation scale, this is the correct pressure scale, absolute value of pressure. Okay. Absolute value of pressure, you will expect this to be the scale. Okay. Technically, the absolute value of pressure will be this plus some constant, you can add any arbitrary constant, but I am saying that okay, that arbitrary constant I do not care about. Okay. You may have this situation close to the sea level or maybe in upper atmosphere. Okay. Whatever rho naught G L is there, that is my pressure scale in this problem. When you substitute P naught over P naught is rho naught G L, then let us see what you get here. So, P naught over rho naught P naught over rho naught U square, where your U square you can get from here. What do you get? P naught, which is rho naught G L over delta rho over rho naught G L times a rho naught also. So, what is this? This is simply rho naught over delta rho. So, both of these guys have a rho naught over delta rho. So, the equation is, so left hand side is whatever here, it is equal to minus or rho naught over delta rho minus del star P star plus rho star G star, and then you have a 1 by Re of the viscous terms and the LHS. And now we see something with epsilon appearing in the equation. This is 1 by epsilon. Okay. We took delta rho by rho naught as epsilon, this is 1 by epsilon. So, the equation similar to continuity equation, the momentum equation will become something like this. So, you have a rho star. So, I am going to write this as d u star over dt star, okay, equals rho naught over delta rho, which is 1 by epsilon minus del star p star plus rho star g star, and then a plus 1 by Re the viscous terms. Let us write them 2 del star dot S star minus 2 by 3 del star So, multiply this equation. So, this is rho naught by delta rho, this is 1 by epsilon. So, multiply this equation with epsilon and what do we get? We get at leading order we will get this equation. Okay. Actually, before we substitute at leading order, we have to substitute the hold on, let us not do the substitution just yet. So, this P star just like we did with rho, we know pressure is going to be some P naught plus P prime. Okay. Pressure is going to change whenever your flow takes place. Okay. Only in hydrostatic scenario your pressure has this rho naught G H variation. The moment there is flow, pressure is going to have some fluctuations in it. So, just because there is flow which is happening due to density changes, the pressure is also going to change. So, the pressure is going to have some fluctuations P prime. So, P star, so instead of writing P naught I am going to write here as P bar. Okay. P naught is a scale. So, I am going to write it as P bar. So, I am going to write P star as P bar star plus a P prime over P naught.
Density you had written rho naught.
Hmm?
Density.
Density is constant, but in that hydrostatic case the base density is constant, but the base pressure is not constant, right, because the base pressure will vary with height. Okay. The base pressure or the base value that you are, so it is like the density might be something like this. So, let us say this is y, this is rho, this is your rho naught, density might be something like this. Okay. Density might be something like this, but the pressure will be, okay, let me make it here, the pressure will be what, decreasing, right. So, pressure will be something like this. Okay. So, that is why I have not written P naught, this is P bar which is the linear line plus some fluctuations. Okay.
P bar is dependent upon y.
Yeah, P bar is that hydrostat, and that is what we will get from this equation. When we separate the powers of epsilon and derive the leading order and order epsilon equations, we will get that P bar is basically that hydrostatic variation. And now P prime and P naught, we know that pressure fluctuations do not have the scale of P naught. Pressure fluctuations will pressure fluctuation scales will actually be something like, let us say, rho naught u square. Okay, because this pressure is, the pressure fluctuations are taking place due to velocity fluctuations which have this order. So, what is the correct pressure fluctuation scale going to be? What is the correct pressure fluctuation scale going to be? So, the correct pressure fluctuation scale delta P is, let us say, rho naught u square, right, which will be delta rho times G L. And now, when you compare it with P naught, and so this you write as P bar star plus delta P over P naught P prime over delta P, we write this as P bar star plus what is delta P over P naught, delta rho over rho naught actually, P prime star, P star is this. Okay. And now we are going to substitute that here in P star instead of P star here, and then we can separate out the.
Delta P is equal to rho naught u square. Where did we get to?
So, what is this pressure fluctuation happening due to? Why is there a pressure fluctuation?
Due to flow. That is due to density change.
Yeah, and so basically what you are saying is pressure fluctuations are due to density fluctuations.
So, but should we not? Achha,
Okay. So, every time I am doing these things, I am using that what you have considered to be dimensional analysis, where you just say, okay, this is a function of this and this quantity, so what is the pi group? So, every time I am writing these intuitive formulae, I am basically using that dimensional analysis thing that you know. Okay. So, I am trying to reinforce that concept, that dimensional analysis concepts that you know, the pi group forming and everything, they are used for determining the relevant scales of the problem. We are determining relevant scales through that. Whenever I say in words that pressure fluctuation is happening due to flow, I am saying that the pressure fluctuation is a function of density and velocity. And then I am asking you, okay, what is the pi group regarding related to this? That is delta p over rho naught u square, right? Okay. So, every time I am writing these things, I am basically doing that dimensional analysis where you take then m l t, make the powers of m and l and t 0 to make a pi group. I am doing that basically. Okay. So, maybe in the next class I will continue from here. We will substitute this p star here and then separate out the equations. So, if things are seeming a bit more advanced, then